So now we need to study the normal distribution as a continuous probability distribution. So we touched on this briefly last lesson, where we were talking about all the different types of continuous probability distributions, at least the primary ones. I mean, there's all different types. So we talked about uniform, we talked about exponential, and we talked about normal. And so now we need to study normal a little bit closer, and really learn how to work with a normal distribution as it relates to a continuous probability distribution. So something to understand with a normal continuous probability distribution, it's probably the most important one of all. Remember, normal means that we're bell-shaped, okay? So we have this bell-shaped distribution. We still see this bell-shaped distribution really all over the place, which is why this is one of the most widely used ones. You know, when it comes to uniform or exponential distributions, they don't occur as often and in many places, as the bell. You know, psychology, business, economics, science, nursing, math. I mean, these all are places where the bell curve really comes into play. So, you know, this is why this is probably one of the more important continuous distributions that we can come up with. You know, here's a little quote. If you ask enough people about their shoe size, you will find that your graph data is shaped like a bell curve and can be described with a normal distribution. Something as simple as shoe size. Shoe size can be normally distributed. So we're going to use this a lot. So when you're working with a normal distribution, you have to really work with two parameters. Parameters, remember, are numerical measurements from a population. And so mean, that's one. Standard deviation, that's the other parameter. Okay? So when we're dealing with a normal distribution, we're also going to have to work with those two parameters. One thing we've talked about is that the mean always falls directly in the middle of the bell distribution. So the mean sits right there in the middle. Cut your bell-shaped distribution into two equal halves. This half is equal to this half. So 50% of your data will be here, and 50% of your data will be here. Okay? We've talked about how the entire area under the curve is equal to 1. Well, if the entire area under the curve is equal to 1, then that means if you cut it in half, this would be 0.5 and this would be 0.5. Okay? In terms of creating this distribution, it's a fairly complicated formula to describe this probability density function for this curve. This is the formula that will generate this curve. It's not something we're going to need to use. I mean, I'm just showing it to you because it is a fairly complicated function. And everything we're doing throughout this section and sections in the future that deal with normal distribution as a probability distribution and finding areas and probabilities, it's not as simple as we're going to make it in the real world. We've simplified it so that we can do it. But the mathematics behind a lot of the stuff that we're going to be doing is fairly complicated. And I've said this before. There's a lot of calculus behind all the things that we're doing here. We're not going to see the calculus happening, but there is a lot of background work that happens, you know, behind the scenes. And the further you study math, if you do get far enough in it, you'll start to understand how it all comes into play. But you don't need to memorize this formula. We've made it so that an introductory statistics course doesn't require advanced mathematics because a lot of that is done. We would have to learn how to read some tables where the mathematics has been done already. All right. What we largely do to deal with normal distributions is to really work with what we call a standard normal distribution. Okay? A standard normal distribution is a normal distribution, bell-shaped curve, okay, that works on the standard z-score scale. So that means that the mean is 0 and a standard deviation is considered to be 1 unit. Okay? That standard scale will allow us to work with multiple normal distributions without having to constantly change the calculus behind the values we're getting. Okay? So it's a standard way of working with normal distributions. So if you remember from z-scores, this was your formula for z-scores. We talked about that previously in Chapter 3. And it was a simple formula to calculate a z-score. What it does is it takes your standard scale, which will have some random mean, which could be any value depending on your problem, and a standard deviation, which could be any distance away from the mean, would be one standard deviation away from the mean here and here, okay? And it standardizes it, and it says instead, what we're going to do is we're going to make the mean 0, the center of this, and one standard deviation will be 1 unit away from the mean. And so we'd be at -1 and +1 here, okay? And then if we were another standard deviation, we'd be 2 standard deviations, so 2 units. So a z-score of 2 and -2. And so a standard normal distribution makes this scale right here a z-score scale instead of just a random scale of values based off of some random mean and some random standard deviation. So a quick just review of z-scores, right? So if we look at z-score for a given x value when x is 1, this notation right here is a standard notation for telling you you're dealing with a normal distribution. So your random variable x is described by a normal distribution, hence the n, where the mean is 12 and the standard deviation is 3. So that notation is just telling you that. And in which case, if I wanted to turn my z-score, my value x equals 1 into a z-score, I would plug that into this formula where x is 1, the mean is 12, the standard deviation is 3, and I would get a z-score of -3.67. So what this is telling me is that 1 is -3.67 standard deviations away from the mean. Or I should say 3.67 standard deviations away from the mean on the lower end. So the mean was 12, the standard deviation was 3 units, okay? So that would put me here at 9 and 15, would be 1 standard deviation away. Another 3 units away would be 6 and 18. And these are 2 standard deviations from this mean, and so on. But if I have a value of 1, which is all the way down here, in terms of the standard deviation, okay, it's not a whole number standard deviations away. It's 3.67 standard deviations away from the mean. That's what a z-score of 3.67 means. And the fact that it's negative means it's below the mean, okay? Because a z-score of negative values is below the mean, and a z-score of positive values is above. And we've gone through this back when we talked about z-scores. So if we were to, say, look at another example, some doctors believe that a person can lose 5 pounds on average in a month by reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution where x is the amount of weight loss in pounds by a person in a month. Use the deviation of 2 pounds, okay, 2 pounds, and fill in the blanks. So we have a normal distribution where the mean is 5, the average number of weight loss is 5, okay, and this deviation is 2, okay, in this normal distribution. The z-scores don't just apply to normal distributions, but that's what we're talking about now, so that's why this is all normal distributions. So anyway, suppose the person lost 10 pounds in a month. What would 10 pounds be as a z-score? Well, you would plug 10 into your z-score formula, minus the mean of 5 over the standard deviation of 2, and you would get 5 over 2, or 2.5. So your z-score for 10 pounds would be 2.5. That's if you lost 10 pounds. So the z-score tells you that x equals 10 is what? The z-score of 2.5 tells you 10 is 2.5 standard deviations to the, since it's positive, to the right of the mean, which was 5. Okay? So this is how you have to remember about z-scores, is how they work. Then we get into something called the empirical rule. Now, the empirical rule is something we could have learned way back in Chapter 3, and oftentimes in statistics it's covered back when we first start talking about mean and standard deviation and relating distribution to all that. But I chose to bump it back a little bit into this section. So what it says is this. Empirical rule says if you have a normal distribution, okay, if your random variable has a normal distribution with some random mean and some random standard deviation, okay, you can find out what percentage of your data would fall within a certain amount of deviations from the mean. Okay? If you are one standard deviation away from the mean, so the mean's always in the middle, if you go one standard deviation on either side and you look at how much information should fit in there, this empirical rule says 68% of all your data should sit right there. Okay? If you were two standard deviations away from the mean, 95%. So if I'm from here's two standard deviations below the mean, here's two standard deviations above the mean, 95% of all my data should be in there. Which is when we talk about something being usual. We said, back when we talked about standard deviation, we said most of our data should be within two standard deviations away from the mean, regardless of the distribution. And this, specifically for normal distributions, 95% of your data should be in that two standard deviation window. And that's, again, what the empirical rule is stating. And three standard deviations, 99.7% should be in that space. And then since it's a symmetrical picture where it's split equally in half, we can then get all these little individual measurements here for all this space. It still all adds up to our 68, 95, and 99.7. But this is what your empirical rule states. Now, we're going to find out where all these percentages came from, right? They come from this probability distribution and finding the area. But this is just the building block of it, and memorizing these three different percentages can be very helpful. So here's an example. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. So the mean right here is 100, and the standard deviation, so that's your mean, and your standard deviation, I like to run it off to the side, is 15. Okay? What percentage of IQ scores are between 70 and 130? So 70 would go this way, and 130 would go this way. Well, I have to know how many deviations away from the mean those are. Okay? This one standard deviation is 15. Well, if I could find the z-score for each of these, 70 and 130, okay, I can find out how many standard deviations away it is. And since it's a bell-shaped curve, the empirical rule could tell me that. And so if we look at this, if I turn 70 into a z-score, I have 70 minus the mean, which is 100, over the standard deviation, which is 15. I get negative 30 over 15, which gives me negative 2. So that's two standard deviations to the left of the mean. The negative means to the left, and the 2 is two standard deviations. So this is basically right where 70 falls in terms of the standard deviation. 130, well, the same thing, right? If I do 130 minus the mean over the standard deviation, I'm going to get 30 over 15, which is 2. So 2 would be two standard deviations, but above the mean. So I'm here. So 70 and 130 are two standard deviations away from the mean. So I want to find out what percentage of people have IQ scores in that range. Well, empirical rule says 95% of all people should have an IQ score in that range, because 95% of your data should be within two standard deviations of your mean in a Bell distribution. Here's another one. Final exam scores in statistics class were normally distributed with a mean of 75 and a standard deviation of 5. So, a normal distribution, mean of 75, and a standard deviation of 5. Okay, this is standard deviation symbol. Find the probability a randomly selected person scores less than 65 on the exam. Well, here's 65. And less than 65 would be here. So we would have to say, well, in terms of the standard deviation, 65 the z-score for this would be 65 minus 75 all over 5. Well, what's that? That's 10, negative 10, sorry, divided by 5. So that's negative 2. So that right there is 2 standard deviations below the mean. But I know between 2 standard deviations above and below the mean, so this would be 85 and 65. I know in here, 95% of my data should be there, right? That's something I know. So how am I going to find out how much data should be less than 65? Well, remember, this picture is symmetric. It's split evenly in half. So this piece and this piece are equal. And if I know the middle is 95%, these two pieces combined should be 5%. And if they're equal, then if I cut that 5% in half, that means that should be 2.5%. That's a percent. The question asks for probability, and this is what you're going to have to make sure you do when you answer questions, answer them appropriately. I turn this percent to a probability by moving the decimal place back 2 spaces. So the probability that x is less than 65, okay, would be 0.025. Again, just using that empirical rule. Now, the problem comes in, well, what if it's not 65? What if it's 63? And now it's not a whole number of deviations away, because the empirical rule only says 1, 2, 3 standard deviations. But what if you have a z-score of 2.7? Now you're 2.7 deviations away. Now the empirical rule kind of starts to not give you enough information. There's only so much you can get there. But we can get these areas, which are probabilities and even percentages, by looking at a continuous probability distribution table that works with normal distributions. And this would be your table, okay? So we have this table. I have it linked in our course. I suggest you download it and print it out. I don't like looking at this on the computer screen. When I work with this, I'm going to work with it so many times. I like to have it in my hands and use a ruler to match up my values. But one thing we're going to learn here is that this table, someone already did all the calculations in terms of the areas for us. Okay? And the idea here is that we need to just find those areas for a given problem. Right? One thing you need to understand is that when I give you those percentages in the empirical rule, they're all rounded percentages, 95%, 68%, even the 99.7%. Those are rounded percentages. This table will give us an even more accurate value for the space inside the Bell distribution. And these are even rounded, but at least they're going to give us up to 4 decimal places. So a little less rounded than the other ones. But they should be very close to what the empirical rule said. So anyway, how does this table work? Well, the way this table works is it says if you look up a z-score in your Bell distribution, this will tell you what the cumulative area to the left of that z-score in a standard normal distribution will be. And it gives you everything based off of a 2 decimal place z-score. Okay? Z-scores have to be rounded to 2 decimal places to use this. So our z-score that we were just working with in the last problem was a z-score of -2. And that was the test score of a 65, right? And in 65, I want to find people who scored less than 65. 65 as a z-score was -2. And I want to find the area to the left of that. Well, I use the empirical rule to give me the answer. But I could use this table to also give me that answer, and this would be actually even more accurate. So how do I do that? Well, the z-scores are listed along the side and the top here. The first decimal place is listed along the side, in which case -2 as a 2 decimal place number would be -2.00. So the first decimal place is 0, so -2.0. So I'll go down to -2.0, which is here. Then the second decimal place is also 0. And so I'll match that up, and here, this is the answer I get. What that answer is it's a value of the area to the left of that z-score in a bell-shaped distribution. So this is telling me that the area to the left of -2 as a z-score in a Bell distribution should be 0.228, 0.0228. Okay? So if I draw that picture again, and I say, okay, mean was 75, 65 was the score I was looking at, and I was trying to find this, rather than use the empirical rule, which we were able to do, but remember, the empirical rule is rounded. It's a rounded value. We can get even better accuracy by using this table. If we convert this to a z-score, which we did, and we said the z-score for 65 was -2, that table we just used says that I can look up that -2.00 and find the area to the left by using the table. And it told me that area was 0.0228. So the probability that someone scores less than a 65 could be 0.0228, which isn't the exact value I gave you just a few minutes ago, because that other value was based off of a lot of rounding happening. And I said 2.5% or 0.025. Ultimately, if we can avoid the empirical rule and we can get the more exact value out of this table, I would like to do that. Okay? That's the most exact value. The reason why the empirical rule starts to fall apart is because you have a rounded value mixed in with other rounded values, and the more you round, we've talked about this, the more things get thrown off. Where this is as accurate as you're going to be able to get without doing all the calculus yourself. Okay? But where this number came from, calculus. That formula I showed you a little while ago that talks about how you get this bell curve, that was very complicated, and some calculus is how this number comes about. So anyway, this is how we're going to find areas in a normal probability distribution, through z-scores and looking at the z-scores up in that table to find area to the left. But we know from the exponential distributions that even though you can get area to the left only from your formula, or in this case from the table, we can use that to find all sorts of areas to the right, in between, and obviously to the left. Here's an example. Again, dealing with the same one. What percentile would a student be in if their test score was a 65? Okay. What percentile would a student be in if their test score was a 65? So remember, what did we just do? We said the mean was 75. That was your mean. Your standard deviation was 5. The score we're talking about is 65. We found out that this area is 0.0228. Or we could say, move the decimal place, 2.28% is, the area. You look at it as a percentage. And then we got to ask, okay, what percentile would this score be? Well, how do percentiles work? Percentiles divvy your data up into how much is less than that. So if I'm at the 45th percentile, P45, 45% of my data is less than that, and 55% of my data is more than that. That's what P45 does. Well, a score of 65 separates the bottom 2.28% from all the rest. So what percentile would 65 be? The percentile would be between 2 and 3%. So P2 would be the percentile for a score of 65. So you don't want to be in the score of 65, right? You don't want to be in this bottom 2% of people scoring on this statistics test. How about we keep doing the same thing again? How about to find the probability that a randomly selected student scores more than an 85? Okay? All right. Same problem, normal distribution. The mean is still 75. The standard deviation is still 5. But 85 is now over here. Okay? 85 is right here. So what I want to do is how many people find the probability that someone scores more than that. So I want to find this area. All right. Well, that table that we just looked at will only give me the area to the left. So this yellow area. And I can convert 85 to a z-score, which is pretty easy to do. It'd be 85 minus 75 all over 5. In this case, that's going to be, what, 10 over 5. So that's going to give me 2. Okay, so I have a z-score of 2. And I could figure out what this will be. And because my picture is symmetric, I can just use everything I've already done to get that answer without much more work. But we're going to go through this from scratch. The table will tell me how much fits here. Okay? But knowing that the entire area is 1, this entire area here should be equal to 1, this area can be found by doing 1 minus the yellow. Okay, the area to the left. I write yellow because that's what I colored it in as over here. But 1 minus that yellow, the area to the left, okay, should give me the area to the right. So let's look at the table. Now we have a positive z-score. So when you look at the table, there are 2 parts to the table. One part where we deal with z-scores that are positive, and the one we looked at before, all these z-scores here were negative. So anyway, our z-score is 2.00. So I go 2.0, and the second decimal place is 0. Match it up. There we go. 0.9772. Okay? 0.9772. So if I have my bell curve, I have this z-score of 2 here. This area down here, which I shaded in as yellow just a few minutes ago, that table tells me that that should be 0.9772. So this area here should be 1 minus 0.9772. In which case, what do we get? We get 0.0228. So the probability that someone scores greater than 85 is 0.0228. Or we could say 2.28% of all people get more than 85 on test. Okay? I can convert, all I did was convert this to a percent. And you're going to have to be able to do that. Switch back and forth between probability and percent. Area, probability, percent. Eventually we're going to talk about proportion. They're all essentially one and the same. It's just a matter of how you present the number. But anyway, that table giving me area to the left can also help me find area to the right. All right, what if I wanted to find the probability that someone scored between an 85 and a 90? So between an 85 and a 90. All right. Well, here's my picture. The mean was 75. The standard deviation was 5. 85 is here. 90 is here. And I want to go in between the two. Okay? So how am I going to do that? Well, I need to know the z-score for 85. Well, we already figured out that z-score is 2. I need to find the z-score for 90. Well, I have to calculate that. That'll be 90 minus 75 over 5. Again, mean standard deviation was 75 and 5. So what am I going to get here? I'm going to get 15 over 5. Okay? So that's going to be 3. So that's a z-score of 3. So what are we going to do? Our table will give us area to the left. So if I look up 85, I can get the area to the left here. We've already done that. We found that that was 0.9772, right? We just did that in the last example. I can look up a z-score of 3. That's for 90. And that'll give me area to the left of that, which will be all this area down here. The problem is I'm counting this green area twice, right? In the blue answer, I have the green area, and then I have the green area. So to find the area in between, if I do blue minus green, which is basically the bigger area, minus the smaller area, that should give me the area in between. Okay? Well, I have to look up 3 because I don't know what the area to the left of 3 is unless I look it up in the table. And once I find that, I subtract the 2 areas and I'll get the area in between. So we use our table, 3.00. So 3.0 is here. The second decimal place is 0 again. The second decimal place was, I don't know, 5. So 3.05. I would then match that up there. And that would be my answer. But that's not what it was, right? It was 3.00 even. So there is my answer, 9987. So 9987. So it was 9772, 9987. So if I look at it here, right, 85, 90, 9772 was the green area. The blue area was, so that blue was the area to the left of the z-square of 3, so it was 9987. So that's this blue area, so let's say 9987. So if I take 0.9987 and subtract 0.9772, that'll tell me what the probability of getting between 85 and a 90 would be. So X is between 85 and 90. So we end up with the difference between these two being 0.0215. So the probability that someone scores between an 85 and a 90 would be 0.0215. Or we could say that this area is 2.15%. Oops, that's a mess. 2.15% of the whole, or 2.15% of all people will score between 85 and 90. So here's another example. So suppose the average number of hours a household personal computer is used for entertainment is 2 hours a day. Okay? So the average is 2 hours a day. Assume the times for entertainment are normally distributed. These are all key words here. And the standard deviation for times is half an hour. Find the probability that a household personal computer is used for entertainment between 1.8 and 2.75 hours a day. So what do we have? Well, what we have here is a normal distribution with a mean of 2 and a standard deviation of a half, so 0.5. Okay? And we're trying to find the area between 1.8 and 2.75. So convert 1.8 to a z-score. Convert 2.75 to a z-score. I will then be able to use my table to find the area to the left of 1.8 as a z-score and area to the left of 2.75 as a z-score. Okay? I can't just look up 1.8 and 2.75 as hours of entertainment in my table because those are just random values based off of hours. I have to convert them to the standard score so that when I have weights in the next question or I have test scores in another question, I don't have a different table for each one. I have one table and it's all converted to z-scores. So I look at this z-score and I'll say 1.8 as a z-score would be 1.8 minus 2 over 0.5. And 2.75 as a z-score would be 2.75 minus 2 over 0.5. So I do those calculations. What I end up with is 1.8 as a z-score would be negative 0.4, and 2.75 as a z-score would be 1.5. Okay. So now I'm going to look up these two z-scores in my z-score table, and I'm going to find the area to the left. But remember, I want area in between. So I'm going to have to find this bigger area, which is to the left of 2.75, subtract out this smaller area, which is the area to the left of the 1.8, and that should give me the area in between. So bigger area, which is to the left of this, minus smaller area, which is the area to the left of this, and I'll get the area in between. So here we're on the positive z-score side first. We're looking up a z-score of 1.5. So 1.50, so you go down to 1.5. Second decimal place is 0. That's the area we're working with. So 0.9332. That's the area to the left of 1.5. Then I go to the negative z-score side. I have to look up a negative z-score of negative 0.40. So 0.4, and then 0 is the second decimal place, so we're right here, and we get an area to the left to be 0.3446. Okay? So if we look at the areas, again, this area here, 0.3446, the area to the left of 2.5, that area is 0.9332, so the area in between would be 0.9332 minus 0.3446. Okay? And the answer becomes 0.5886. So we could say the probability that that personal computer is used between 1.8 and 2.7 hours, the probability that that happens would be 0.5886, or we could say 58.86% chance that the computer is used between 1.8 and 2.7 hours. Here's another one. Suppose that the incubation period, that is the time between being infected with a virus and showing symptoms, for the Ebola virus is normally distributed with a mean of 12 and a standard deviation of 4.5 days. Obviously, you could see how this could be very relevant to the world today as it relates to viruses. So, find the probability that a randomly selected case demonstrated symptoms in fewer than 7 days. So, key words here. Normally distributed with a mean of 12 and a standard deviation of 4.5. Okay. Normally distributed with a mean of 12 and a standard deviation of 4.5. What's the probability? Okay. What's the probability that a randomly selected case had symptoms in fewer than 7 days? Okay. So 7, fewer than 7. That's what we're looking for. If we're looking for a probability, remember, we're looking for an area. Okay? So, we need to convert 7 to a z-score. Once we convert 7 to a z-score, we need to find the area to the left of that z-score. So, z-score for 7 is 7 minus 12 over 4.5. If I round that to 2 decimal places, I get negative 1.11. So that's the z-score I'm going to look up in my table. It's a negative, so make sure I'm on the negative side. And I want area to the left because I want fewer than 7 days. Okay? So the probability that a randomly selected case demonstrated symptoms in fewer than 7 days. So we look up a z-score of negative 1.11. So here's negative 1.1. Second decimal place is also 1, so match that up, and I would get this value right here, so 0.1335. So that tells me in my picture, if 7's turned into a z-score of negative 1.11, that this area is 0.1335. So the probability that the incubation period is less than 7 would be 0.1335. This example is a little less serious. So Girl Scout Thin Mint cookies have a mean size of 0.25 ounces. Find the probability that one randomly selected cookie has a size of more than 0.27 ounces. If the standard deviation is 0.03 ounces, then assume we have a normal distribution. So, key words. The mean is 0.25 ounces. The standard deviation is 0.03 ounces. We have a normal distribution, and we're looking at something to be more than 0.27 ounces. Okay? So I always feel that the picture is the first step in this process. Mean, right in the middle, 0.25. Standard deviation, I just write it off to the side, 0.03. 0.27 would be sitting on this side of 0.25, on this side of the mean, and I want more than. So I want to figure out what that area is. All right, well, what can I do? I can convert this weight to a z-score. You always have to convert to a z-score, because that's the only way we can use the table. So I'll take 0.27. This is a 0.27 minus 0.25, which is the mean, over the standard deviation is 0.03, and I'll come up with my z-score. So 0.27 minus 0.25 divided by 0.03, rounded to 2 decimal places, I get 0.67. Okay, 0.67. So now when I look this z-score up in my table, it will tell me the area to the left. I'm a positive z-score, so I'm on the positive side. I look it up, 0.67, and I come up with an answer of 0.7386. So this is 0.7386. Okay, so 7.7486. 0.7486. Okay. So then if I want to find the area to the left, to the right, because I want more than, I do 1 minus 0.7486, and the probability that a randomly selected cookie has more than 0.27 ounces would be that difference, 1 minus 0.7486, which brings me to 0.2514. Done. All right, one more question here. This one, though, is going to be different. Look at the wording of the question and think about what it's really asking us to do. It's talking about In-N-Out hamburgers. If you ever had an In-N-Out hamburger, you know that they're extremely delicious. But let's suppose that the number of French fries in the batches at an In-N-Out are normally distributed with a mean of 42 fries and a standard deviation of 3.7 fries. So we're looking at the number of fries in a batch of fries. Let's say a large fry, whatever. But what do we know? They're normally distributed with a mean of 42 fries with a standard deviation of 3.7 fries. Because you don't get the same amount of fries every single time. So right away I'm going to do this. Normally distributed, mean of 42, standard deviation of 3.7. Okay. So then, let's read the rest of it. Your friend tells you that the In-N-Out employee was flirting with you. And if you end up with a French fry count that is in the top 5% of all French fry counts, then that means that they really were flirting with you and they gave you some extra fries. Okay? Well, what number of fries would put you in the top 5%? Okay? How should we characterize the top 5% of French fries? So here's the top 5% of French fries per batch, right? How many fries would be that dividing line between the bottom 95% and the top 5%? Obviously, this is a ridiculous question, but that's not the point. The point is, look at what this question is asking you. This is the exact opposite of every question we've looked at so far. Every question we've looked at so far, we have been given this amount, the number of fries or the score or whatever, and we had to figure out what the area is. Here they gave us the area. 95%, 5%, that's percentages. I can turn that into a decimal, 0.95, or in this case, 0.05. And I'm trying to find how many French fries would be in my large fry that would put me in the top 5%. And therefore, the employee was giving me some extra fries, most likely. Well, again, this is the opposite of the questions we were given before. So what we're going to have to do is everything in reverse. We can't go straight to a z-score and then look at the chart and find the area. We have an area, so we need to start there and then find the z-score. Then once we have the z-score, we need to convert that up to figure out how many fries does that really entail. So we have a z-score formula here that looks like this. What we'll know is the z-score. We will not know the data value, which is represented by x. So what I'm going to have to do is some quick algebra to resolve this equation so I can figure out what x equals instead of z equals. And that's pretty simple. It's going to be that z equals the mean plus z times the standard deviation. So it's just a reworking of that formula. So again, what I'm going to do, I'm going to look up my area in the table to the left, which is 0.95. That's an area. That's going to then tell me a z-score in my table. Once I have my z-score, I'm going to plug that into this formula along with the mean and the standard deviation, and that's going to tell me how many fries should separate the top 5% from the bottom 95%. So let's look at the table. So here's the z-score table, in which case, remember, we have to use the positive z-score table. Why is that? If we're looking for 95% of our data to be to the left of this particular z-score that we're trying to find, then that z-score has to be to the right of the mean. Why? Because the mean would split this into 50% and 50% on either side. So if all this is 95%, that z-score has to be down here, which means the z-score has to be positive. So we're on the positive z-score side of our chart. The z-scores are located around the outside, but we're not looking at a z-score. We know that the area here is 95%, or 0.95. These are where your areas are located, okay? So we're searching through these areas, trying to find 0.95. These are all 4 decimal places, 9500 specifically. And if you keep looking, you look right here in the middle of the chart. Here's 9495, and here's 9505. And 0.95 would fall right in the middle where that star is. Follow that star and the arrow down, and you see 0.9500, z-score is 1.645. Why is that one given to us? Well, because it's a pretty common one, so they place it here, even though it falls in between 2. And the z-score has to be given now in 3 decimal places to be more specific. Let's say, though, that doesn't happen. Let's say we're looking for, we have an area somewhere between these 2 areas. And let's say it's 0.9804. Okay? Well, you're not going to find 0.9804 on the table. You find 0.9803, 0.9808, and 0.9804 is somewhere in between. So what do you do there? You don't have a nice little star that you can follow down and figure out what the answer is. Well, all you're going to do is just go with whatever's closest. So 9803 is closest, so I'm going to use that one and follow the z-score that's associated there. That way and then that way. Okay? But we don't have that, so let's get rid of that. We had this one, and we know that the z-score for this value right here, the z-score is 1.645. Remember, that's the z-score. Now, I need to know, okay, what value in terms of the number of French fries is going to be sitting right there. Well, that's where we have this x equals the mean plus z times the standard deviation, where we resolve that z-score formula. So we know the mean. The mean was the number of fries was 42. We just found the z-score that we were looking for as 1.645, and the standard deviation was 3.7. So if we put that in, that'll tell us what that number of fries is that'll separate the top 5% from the bottom 95%. So I came up with an answer of 48.0865. So, if anything over 48.0865 fries in your container, you would be in the top 5% of the number of fries in your container. Again, this question's ridiculous, but the point of the question is we're working this problem in reverse from all the previous questions. So what you're going to have to get used to doing is reading this table both forward and backwards. Okay? This is where the picture really comes in handy. If you know what you have and know what you're looking for, you'll know how to read this table. Do I have an area, in which case I'm looking for a z-score and then a data value? Or do I have a data value, in which case I'm looking for a z-score and then looking for the area? So if you have a z-score, you start on the outside and you find the area in the middle. If you have an area, you start in the middle and work your way to the outside of this table to build your z-score. Very quickly, you become an expert at reading this z-score chart, forward, backwards, in between, and we're going to be using this pretty much the remainder of the semester. So, like I said, I highly suggest you print it out and have a hard copy of it that you can work with. I don't like looking it up on the computer all the time, but that's my personal preference. You do what you want.